we are going to start some integration. You don't need to write this down. You can if you want. But there are two branches of calculus. So like, what did we deal with pretty much all last semester? Very good. So the first branch is differential calculus, the study of derivatives. The second branch is what we're starting today, and that is called integral calculus. Okay? Differential calculus, do you remember what question it answers? How fast? Integral calculus answers the question, how much? Okay? And in about 2 weeks, we'll see how the two are actually very much related. Okay? There are two inventors of calculus. Do we know either of them? Oh, yes. Newton gets all the credit, though. Newton gets all the credit. He did do a lot of things. It's like, do we know the other inventor? Oh, that was a really good guess. That was a really good guess. Leibniz. Okay, choir people. German. I comes after, right? You pronounce the second vowel. Okay, so Newton and Leibniz, they invented calculus simultaneously but independently, which is pretty wild to me. Newton came at it from a physics point of view, Leibniz came at it from a geometry point of view, and lo and behold, they were inventing or discovering, whatever your philosophy is on that, the same mathematics. Sadly, I feel Newton gets all the credit. I'm Team Leibniz all the way. Okay, so we're going to learn integral calculus backwards today. Usually, you look at like the techniques of a math concept, how to do it by hand, and then maybe you start to look at applications, and then maybe, oh, by the way, the calculator can do all this, right? It's kind of the order it usually goes in. We're going to go backwards. We're going to look at why we learn integral calculus, what it does for us, and we're going to do it on the calculator today. And then as we go on, we'll start to learn how to do it by hand as well and see what the calculator is calculating. Okay. All right. First, a quick recap of summation notation. I would like for you to write this. So sigmas, let's see how much of my videos you watched last year in pre-calc when we went into lockdown. So this is the Greek letter sigma, stands for sum. So you can you use a letter for your index down here. It doesn't really matter what letter you use. K is pretty common. And you can start at any counting or any natural number. Often we start at 1. And then here's where you end. So I'm going to, for this example, end at 4. So if I had the sum from k equals 1 to 4 of 2k, what this means is I would start with 1, plug it in for k, and then add every single term after that, plugging in the integers between 1 and 4 inclusive. Okay, so if I plug in 1 for k, I would get 2 plus sum. Now keep plugging in your k values. If I plug in 2 for k, I would get 4. Plug in 3 for k, I would get 6. Plug in 4 for k, I would get 8. And then you could add up all those, okay, 20. And I would stop there. Does that make sense? Familiar? You can also have infinite sums. So I could go from, say, k equals 1 to infinity. And if I change my formula to like k squared, this would be like 1 plus 4 plus 9 plus 16 plus ... Okay, so you can have finite or infinite sums. Just a quick recap from Algebra 2 and Pre-Calc. What do you think this has to do with integrals? By the way, what question is the integral answer? How much? Definitely a sum, right? Okay, you do not need to write any of this down, but let's talk. So a water pipe bursts and spills water at a rate of 3 liters every minute. That's a derivative, right? How much total water has leaked after 2 minutes? 6. 3 times 2, right? Now let's talk about this. That's kind of an algebra approach. Let's talk about this geometrically. So if y equals r of t is the rate, let's graph it. What was the rate again? Yeah. So what does the graph y equals 3 look like? Yes, thank you for nothing. Straight line. Horizontal line through the y-axis at 3. And how long did we go? 2 minutes. So we started at 0, ended at 2. If I look at the area underneath, or really between the blue graph and the x-axis from 0 to 2, what shape is that? Rectangle with base 2, height of, so area of 6. Okay, that's how we get our total accumulation. We just take the area under the rate function over our time interval. Okay, and by the way, the units would match as well, right? Because you would get 2 minutes times 3 liters per minute. The minutes would cancel, and you'd be left with liters, right? So again, what are we calculating here? What geometrical aspect? Area, right? We found that area. And if I kept going, like if I added more time, what would happen to the total area? It would increase, absolutely. Okay. The thing is that is not a very realistic example, right? Typically things change at changing rates. They usually don't just have this nice constant rate of change of 3, right? Usually they change at varying rates. So what about this? The rate of water flow, still for 2 minutes, okay? The pipe leaks, and now it's recorded every 60 seconds. Okay, can you copy that table in your notes for me? So what does this table mean? So instead of just the rate being this constant 3 liters per minute, what's going on now? The rate's changing, right? And we've gotten snapshots. So right when we start the timer, the water is leaking out at a rate of 1 liter per minute. 60 seconds later, or 1 minute later, we've got a rate of 3, and then 2 minutes, at time 2, we're slowing down a rate of 2, okay? And I've plotted those points, again, time versus rate here, okay? So last time, we were able to make one nice rectangle with that rate, right? Because we just had this nice constant rate of change. Ideas now, like how could I at least approximate the total amount of water leaked? We could connect the dots and find the area underneath. That would be a pretty good approximation, actually. Very good approximation. Let me show you here, too. So one idea would maybe say, okay, just use that first rate for that first time interval and find that area. Use the second rate for the second time interval, find that area, add them up, right? Or we could go the other way around, right? Use the second and third rates, find those areas. Yes, this is actually a great approximation. Connect the dots or average the two and find the area there, okay? So the thing is, though, these are still all approximations because we only got 3 snapshots in time, right? Does that make sense? We only took 3 time intervals. We don't know what's going on in between. So for what we're given, I'd say this is our best method. But to get even better, I would need more snapshots. Do you agree with that? So now, still leaking for 2 minutes, and now I've recorded once every 30 seconds, right? So some options. Use the left endpoints to make these rectangles, right? That's what it looks like using the right endpoints for the heights. This is what it looks like averaging the left and the right. And then this is what it looks like just doing 2 and say, okay, I'm just going to use literally the middle y value. Okay. The idea, though, is whatever method I'm using, I'm basically making rectangles. Even these weird trapezoids I can think of as a rectangle where the height is the average of the left and the right. Okay. So let's write this in summation notation. So I'm going to sum up. Can you write this? Actually, copy that table for me. And let's write in summation notation. So one thing I do want to point out, as I'm using more rectangles, what is happening with the base of the rectangles versus like what I had here? The width. They're getting smaller and smaller, right? So more rectangles means smaller base, right? So let's write one way we could find the area of all these. So let's use K as my index. So K, I'm going to start with the first rectangle. K equals 1. In this case, how many rectangles do I have? 4 rectangles. So I'm going to start with the first, end with the fourth. Now what's the same for all of these rectangles? The width. And the area of a rectangle is basically height times base, right? Length times width. What is the width in this case? 0.5, right? So I'm going to leave some space here, and I'm going to put times 0.5. That's what's the same for each rectangle. Now, what varies? The height. And even that depends on what method I'm using, right? But the point is I grabbed the height from that row. Agree with that? From the rate function. So what I'm going to do is I'm going to say, okay, the height is coming somewhere from this table, depending on what method I choose, right? So it is going to be something from R of t with, I'm going to put a subscript of k, which just says it just depends on which interval I'm on, which rectangle I'm on, first, second, third, or fourth. But it's coming somewhere from that row of R of t. Okay? So I'm getting a better approximation. How come? Better approximation than when I had this table. More data, right? More rectangles. The problem with more rectangles is what? More math, exactly. If I wanted an even better approximation, an even better idea of what's going on, I would need what? More data, right? Oh my God, don't write that. Okay, so now, I have a better idea of what's going on because now I'm taking snapshots every what? 15 seconds, every 0.25 minutes. Do we see that? So let's see if we could write an approximation for the total amount of water leaked now. So I want to take a sum. Can you write that? How many rectangles am I going to have now? Should have 8, right? Because I took twice as many as last time. So let's use K as our index again. So I'm going to start with the first rectangle. What do we want on the top? 8. What's going to be the same for each rectangle? The width. And if I'm in terms of minutes, it would be 0.25 minutes, right? 15 seconds. Okay, so I'm going to put 0.25 as my width. Now the height is going to vary, but the height is always going to come from where? R of t, right? So I'm going to put R of t sub k, again, some y value within that subinterval. And think about your units. Every time you're going to take something from this row times something from this row, so what would your units end up being? Liters. How much, right? How much water leaked, okay? All right, so take a look here. 0.25 is our base. Physics people, or maybe chemistry people as well, what do we call that? That's my change in time, right? You've heard that? Change in time for every interval. What letter do we use? What Greek letter? Delta, right? So this is my delta T. Okay. And then this again is my R of T. Okay. So again, I know I'm taking snapshots every 15 seconds. How could I get an even better approximation? More data. The problem with more data is more math, more work. How many rectangles would we need to get the exact amount of water? Like infinite number, right? I need snapshots every moment, okay? So infinity, that's where limits come in, and that's really the study of calculus, right? What happens as we take the infinite case, the continuous case versus the discrete case, okay? So how can we get the exact amount of water leaked? Infinite number of rectangles, right? So this is what an integral is the sum of an infinite number of rectangles, okay? So here's what we want. We want to take the limit as my number of rectangles, call it n, goes to infinity. And my sum, we took my first rectangle, going all the way to my nth rectangle. And to sum up an infinite number of rectangles, it's going to be height times my change in time. But now my change in time is going to be infinitesimally small. Okay? That's a really clunky way of writing it. So instead we use integral notation. It looks like this. An elongated S for summation. Okay? That's called an integral, that elongated S. We're going to use a definite integral. So from A to B, so this is going to be my start time. This is going to be my stop time. Now you need some things inside your integral. And that's going to be your formula for rectangles, area of rectangles. So I'm going to take the area under the rate function, just like here. And now instead of delta t, remember we went from Greek to, I'll call it American letters, English, right? dt here. Delta t turns into dt. So when you see this integral notation, this just means find the area under the curve of this function, starting at time A and stopping at time B. Okay, we're going to make some more sense out of this here. All right, so let's see if we can set it up. Suppose the rate at which gasoline is being pumped into your car can be modeled by G of T, where G is measured in cubic centimeters per minute. How could we find the total amount of gas? So that's a how much question, right, an integral. After 6 minutes, and we're doing setup only today. Okay, once we get actual functions, we'll make the calculator do the computations. So this was a total amount. Okay, so I'm going to take an infinite sum. Go ahead and write that for me. What was my time? 6 minutes. So if I assume I'm starting at 0, I would start at 0, end at 6. And here, let's say here's my g of t function. You don't need to draw that. But what I'm trying to do is I'm trying to fill in this area with an infinite number of rectangles. Okay? Each rectangle is going to be infinitesimally thin. Do you buy that? And we're going to denote that with dt, okay? An infinitesimally thin moment in time. Just. However, the height of each rectangle varies, right? Depending on if I take this slice it'll be that y value, right? If I take, of course the color's not changing now, this slice, it'll be that y value. The point is, the height changes, but it doesn't just change randomly, it changes based on my function g of t. And that's it. Okay, once I calculate this thing, it would give me the total amount of gas we pumped in. 6 minutes is a really long time, for the first 6 minutes. Let's do our unit analysis. G of t was in what units? Cubic centimeter, I am on green, per minute, okay. That was g of t. T, so change in time. What was time in? Minutes. So when I multiply those, I'm left with just what? Cubic centimeters. Is that a reasonable unit for gas, for volume? Yeah, absolutely. 3 dimensions. Okay. All right, let's try bringing the calculator into it now. All right, so snow is falling at a rate of S of t, where S is measured in cubic centimeters per minute and t equals 0 corresponds to 8 a.m. Calculate the amount of snow accumulation from 8 to 10 a.m. Okay, this is an integral. Why? Calculate the amount, right? So this is a how much, so I'm going to take the integral. What do you want your a, your limit of integration, to be on the bottom? 0. All right, now what is S of t measured in? So where do you think I want to end? Don't say 2. Good. Remember, you need your units to match so that you get that cancellation, right? So I need my independent variable to be in minutes. Well, I'm going for 2 hours, right, from 8 to 10, so that would be 120 minutes. All right, and then I'm going to sum up a whole bunch of rectangles. The height is going to vary, but it's going to vary according to this formula. Okay, it's whatever the y value is there. Okay. So I can either write S of t, or I can just write that whole thing. I'm going to write that whole thing because we're going to put it in our calculators. I'm also going to rewrite it like that. So there's the height formula. Again, each height is different. Times, rectangles are height times what? Width. And what is each width? dt. Tiny. Infinitesimally thin. Okay, you got your calculators? Do you remember what command you used to get derivatives on the 84? Math 8. So maybe not surprisingly, we're going to use math 9. So math, and then you can see function integral there for 9. Math 9. And then you just plug it in. Okay, so I'm going to go 0, 120, and then let's put this in, so it's going to be 0.01. I'm going to use x instead of t, it's just easier to grab. Then do another set of parentheses, sine of x, closing both. Square. Make sure I'm good there. And then instead of a t here, I'm putting what letter? X. Make sure you're in radians, by the way, since I am using a trig function. And I think we're good there. Double check your parentheses. It is going to take a little bit for the calculator to do this for us. Desmos can do this instantaneously. On Desmos, you just type in INT. Does it for you. There it is. So about 35. 35, how many decimal places do I need? 3, so 35.717. What are the units? Cubic centimeters, again, reasonable for amount of snowfall. Okay, 1 second. Virtual students, you have an assignment. You've got 8 problems. So try those and submit in the assignment box.